Thank you very much, Oscar and Ruben. Thank you very much for the kind introduction. I'm honored to be here to be able to speak today at Big Data Spain. My name is PACO. I'm from California. I'm currently Director of Community Evangelism at Databricks. We're moving into San Francisco. We've been in Berkeley, but we'll now be based out of San Francisco, California. I'd like to talk about some ways in which big data is changing, and I feel it is changing very abruptly. And so I want to give a little bit of background as far as what is my basis for this. Personally, I started studying machine learning about 30 years ago. I was at Stanford, and there were opportunities to be working in a certain area of, at the time, what was the AI program, but I was very interested in a particular area of machine learning. As it turned out, the university didn't think that machine learning was academic enough at the time, so my advisor moved on and went and did something else. I went into distributed systems, so I've had a career that, on the one hand, was very largely about distributed systems. On the other hand, I had that background working with machine learning and also more the quantitative basis. Somewhere around 2000, that shifted, and these two fields came together. There was a lot more demand for doing what we now call data science. So for about 10 years, I led teams working in very large data problems, and I'm grateful to have been able to recruit and train and mentor a number of data scientists who are now off leading programs in other major companies in Silicon Valley. Throughout all this, though, I've noted there have been times when the world changed. There have been inflection points. There was one very quintessential inflection point in the mid to late 90s when people started to think very differently about how to handle computing. And that led to what we see now as horizontal scale-out, as big data, as what we have embraced with applications for machine learning. But I sense that we're on the cusp of another kind of inflection point like this. And what will be required, I believe, is, again, as Oscar said very, very well, it's about a change in thinking. And so I would like to present 7 points of the kinds of change in thinking that we see happening, not evenly distributed, but they are happening in certain parts of industry, and they need to be able to be brought forth throughout more of the industry. Okay, so one thing is, it has to do with our idea of where and how we do our computation. Oscar was talking about cloud. The economics of data centers has shifted very drastically. And we're looking at larger and larger kinds of warehouses, of being able to use commodity hardware, which is much more advanced, which has multi-core, has larger memory spaces. I have a picture up here from some of the Google publicity of what the internals of their data centers look like. There are issues that the kinds of big data frameworks that people use popularly in industry do not necessarily embrace the economics of the current data centers. I previously had worked on a project called Mesos and was very much looking at this throughout industry. Another thing also is that the requirements for working with data are changing abruptly. As mentioned, there's all kinds of sensor data that's coming in. As well, there's the microsatellites that are being deployed, a number of different types of Internet of Things, Internet of Everythings, these types of use cases, and they're boosting the data rates through the roof. There's a photo up here that I have from General Electric, and this is of some of their turbines being developed. If I've got my numbers right, the rotational sensors on these turbines for all the commercial aircraft in flight currently generate about 12 exabytes per day. There's an excellent case study about this. 12 exabytes per day, that's thousands of Facebooks. And that's just off of one sensor on one product. So I think that we're already swimming in an amazing amount of data, and in some cases collecting it but not doing anything with it. GE in their case study has shown how much benefit they have of being able to watch and predict early if a jet turbine is going out, but also all of the supply chain that's required for when they have to ground the aircraft, when they have to schedule the maintenance, et cetera. So this is an excellent case. There are so many millions of other types of cases like this. So, change in thinking. One of the biggest changes in thinking, I believe, it has to do with containers. Recently, there are announcements. I was at Google Compute Platform Live about 2 weeks ago in San Francisco, and there are excellent announcements there about leveraging containers. The statistic that came out was that Google launches 2 billion containers per week. And this has been followed up recently by Amazon AWS, making announcements at their event in Las Vegas, I believe last week, also supporting containers. We're seeing this across the board. So if you're not using containers yet, definitely check into this. You need to be using it or you're missing out. But containers are just the tip of the iceberg. What they represent is a lot of foundational work that's been going on in operating systems since the early 2000s. Somewhere around 2006, there was a big change in Linux, having C groups become available. A lot of that was provided by Google, actually. And there are a number of practices that have evolved around leveraging C groups and things atop it, such as LXC and Mesos and Docker and others. Now, I've worked a lot on the Mesos project. I highly recommend that. Some of the benefits that we've learned out of looking at the case studies for Mesos were, number one, there are much greater mixed workloads. And mixed workloads mean a number of things. On the one hand, they provide higher utilization rates or opportunities for higher utilization rates within your data centers. That cuts down your cost basis. Number two, they provide for much lower latency when you're producing data products, because now instead of having one cluster over here and taking all the data and shipping it to a cluster over here, and then taking it and shipping it over to some application over here, instead you can mingle them all together right where they're being used. So there are huge opportunities for lower latency. As well, there's a lot less overhead in terms of ops. And frankly, this is the killer. This is the crucial factor that prevents a lot of companies from being able to play in this realm, is whether or not they can actually hire enough of the ops people. So I believe that containers are a very good way of being able to get into this. There are excellent case studies coming out of Twitter, how they used Mesos to move up to their IPO. Also case studies out of eBay, Netflix, a number of startups, et cetera. Google is talking more about what they're doing with the Borg and Omega projects, Omega being the most current one. More sophisticated than Mesos, but a similar idea. IBM has something like this called Platform Symphony. I've heard a little bit about Autopilot from Microsoft. I don't know a lot about it, but also in this area of how do you manage a warehouse scale data center. Now, I think the problem here is that the major cloud users, such as Amazon and Google and Microsoft, these people who've known, these companies who've known how to use clouds for so many years, I think that they get this. And certainly there are a lot of, in my background working with clouds, there are a lot of companies that can come in and leverage it. But still, so much of the world is thinking about VMs, thinking about how computation is defined by VMware, and that has to change. There's a very popular project called Docker. Is anybody here using Docker? Maybe? Okay. There's a very popular type of containerization called Docker. And of course, this is getting great support from Google Compute Platform, as well as now from Amazon and others. DigitalOcean is another one that supports this very well. One of the problems, though, of just looking at things in terms of containers is that you still need to manage what's outside of the container, especially the shared resources. And that's still problematic. There are ways of doing microservices. It's not well defined yet, but this is a growing area that needs much more definition. I'll point here to a link if you want to learn more about Mesos. Here's some presentations that I've had. As well as there's a company about this called Mesosphere, which is helping to commercialize it. And in terms of looking outside of the containers, how do we manage more of, like I say, microservices and other types of integrations? I'll point to a project out of London called Weave, which I think is also very good. So, one major problem is that if you are at Google or IBM or Microsoft, and you have these very sophisticated practices in terms of using clouds, that's great. But what if you're at a major bank? How do you leverage this to handle the real world compute loads that you must do? That's an organizational problem. It requires a kind of change in thinking. And it's going to be a fairly drastic change in thinking from contemporary ways of looking at IT. Okay. So that leads into clouds. And forgive me for being biased, but in 2006, I had the great fortune to be one of the early people working with Amazon AWS when they first rolled out publicly. And our team created one of the first 100% cloud architectures at the time. And then a year later, well, that was in 2007 we created that, and then a year later in 2008, our team was one of the largest Hadoop instances in the cloud. So we got to work very closely with Amazon, and forgive me for being biased, but I really like clouds. And for now, for 8 years now, going on 9 years, I've had a lot of arguments or debates, if you will, with people about what are the economics of cloud? When does it make sense to be in cloud? And frankly, I don't really see much these days for where it does not make sense to be in the cloud. And in particular, I'll point out one statistic. When you look in the US, there's a typical utilization rates for data centers in the US. They're typically in single digits. About 8% is what I hear. And that's an extremely poor usage of resources. That represents a lot of machines. That represents a lot of people managing them. It represents mostly a lot of power to run these. Because for every dollar that you put in to running one of these data centers, you're only getting 8 cents out of it. But yet that's contrast with a wonderful remark that I saw at GCP Live a couple weeks ago. And one of the responses to what was being presented by Google was this gentleman here, Ron Harlov, said, in 5 years, programming one computer instead of a whole data center will be as foreign, as odd as writing microcode is today. And I think it's very true. I think we have to get away from thinking about programming individual hosts. And instead think about what can we do with clouds, and again, running containers and microservices, et cetera, on top of them. That's a change in thinking. Now, for companies that are used to spending a lot of money on throwing away power, they're used to cheap energy rates, and they have staff that are accustomed to thinking in terms of individual hosts and VMs, clouds will not be a familiar territory. This will be something very different. And frankly, from my experience, cloud is not as much about software as it is about sophisticated engineering practice. You really have to raise the bar to do something effective in the cloud in terms of the discipline and the training that you have for your engineering staff. Now, in my own background as a data scientist, that recalls a lot of the shift that we went through in the industry, moving from, say, business intelligence to data science. There was much more rigor, there was much more of different types of technologies involved, and much more discipline required to be able to come out with the end results. So it was not simple, but it's a change in thinking. Now, I feel that the majors, again, they understand this, the Googles, the Amazons, and the other companies that are just another tier below, like the Facebooks, the Twitters, the LinkedIns, they can go off and create their own clouds. They have enough money. They can also hire hundreds of very sophisticated operations engineers because they have the money to go out and get them. But what about the rest of the industries that are trying to come in? They probably won't be able to get those big operational staffs. They probably won't be able to acquire what it has taken Google and Amazon and others over a decade to learn. So we must understand, how did these other industries get onboarded? How they proceed, that becomes a key question. I will point to something that's very interesting, very encouraging. If you haven't seen it, I would recommend this research at Stanford. Christina Delimitriou had a project working with Mesos, and they worked off of cluster traces from Twitter and Google. They were able to use very sophisticated machine learning to come up with predictive analysis of what resources in a data center would be required across all the applications running. And they were able to go from, for instance, with the Twitter case, they were able to go from a 20% utilization to over 70% utilization, which is just outstanding. What they found is that people tend to over-provision. The managers who are deciding how many resources to use tend to be conservative and over-provision their resources by about 500%. And by using the machine learning to augment, they were able to get that down to about 10% over-provisioning, which is a huge game changer. But again, this will take a lot of sophisticated engineering as well as a lot of sophisticated machine learning to make this happen across the industry in general. Another thing, a change in thinking, has to do with abstract algebra. And there was a great question on Stack Overflow. It was early last year. And the idea is that Twitter had pushed out an open source library for leveraging abstract algebra. And they were using this for their revenue applications. And some people asked, why is it that Twitter is doing this? How does this make sense? Could you please explain it further? So I'll definitely point to that. One of the data science leads at Twitter, Oscar Boynkin, answered this question. And it's very compelling. It's very enlightening. You can think of applications of abstract algebra as being a way of kind of containerizing business logic. If you have the business logic of your revenue apps, you can leverage semigroup structure, monoids, rings, fields, etc., these mathematical properties, to make your applications run exponentially faster. This is a game changer that Twitter leveraged to be able to do their IPO. Now, if you've never worked with abstract algebra, these areas of mathematics, some of it can be daunting. Here's a nice graph that shows some of the relationships, but in particular, we leverage something called a monoid. When we're working with big data, a lot of Hadoop programmers, for instance, use monoids intuitively when they write the code for MapReduce. But to illustrate it much better, Avi Bryant, who was formerly at Twitter, and also Oscar Boynkin, they have a couple of excellent presentations here that I encourage people to read. The idea is that by leveraging the math, you can make it such that the grouping of the data doesn't matter if you have associativity. Also, by leveraging math, the ordering of the data doesn't matter if you have commutativity. Also, by leveraging monoids in your code logic, if you have sparse data, if you have sparse matrices, graphs, etc., the zeros don't matter. And this has huge implications, particularly for streaming, because now it means you can take the data as it comes in and process it effectively without having to wait and impose a batch window, sort it, do whatever grouping you need, etc. The old ways took a lot of extra time. But if you leverage the math properly, you can get into much more of a streaming kind of process for your revenue applications. Okay. A fourth one has to do with functional programming. And I think that I love working with functional programming, and I have for a number of years. And as I'm going out and teaching people about functional programming, especially with Spark, it's interesting to me. The real theory for this has been around for over 80 years. If you go back into the 1930s, Alonzo Church and others were working on notions of lambda calculus, very formal notions of what could be computed even before they had computers. It took about another 40 years, though, before that became software. And so John Bacchus, who led the Fortran team at IBM, he came up with the idea of applying algebra to understand how to write better compilers, how to look at the algebra of the code itself, something called an applicative system. Spark is a type of applicative system, and I'll show that in a moment. But really, even then, it took another 20 years before anybody found a good use case. And so I would point to Patty Mize from MIT Media Lab. Patty's team, a friend of mine had been a postdoc on her team. They were one of the first to ever put a recommender system on the internet. It was a brilliant idea. It generated a lot of data. It generated enormous amounts of log data. And yet they applied machine learning to the log data to make their applications smarter, and that became a kind of virtuous cycle. And I really point to that as sort of the epigenesis for big data. What we see at Amazon, eBay, Yahoo, Google, etc., what they did with some of the origins of big data and e-commerce in, say, 1997, that was only a couple of years after Patty Mize's team. And that's what really started this big data movement. Now, if you roll the clock up another 5 years or so, Google had been working with machine learning at scale on commodity hardware, working with very big data. They had the problem that if you run 2,000 machines for a day, 10 of them will fail. 10 of them will die. So if you have a job that requires 2,000 machines, it's never going to complete because you keep having different machines fail. So they came up with Google File System. They came up with MapReduce. If you read the papers about these, especially MapReduce, they make a big deal about leveraging functional programming, leveraging some of the things from the 1930s, lambda calculus, the maps and the reduces, well, flat maps and reduces. And it was mostly about mitigating risk. It was about the fact that so many servers fail. How can you avoid that? Now, there was another project, very influential, from Microsoft called Dryad Link. And there have been a number of different other projects that have taken inspiration from this. Dryad took it beyond MapReduce and looked at a much more general case of how to work with distributed systems, how to leverage clusters, these warehouse computing scale kinds of applications. Spark, Flink, Scalding, Scooby, Scrunch, there's a number of different types of workflow abstractions now that leverage functional programming that really gain influence or derive a lot of influence from DryLink. Now, the point about using functional programming for big data, there's really two things. One is you do need to use this level of technology if you want to take advantage of all these multi-core and really large memory spaces, the contemporary types of machines that we have in data centers. And number two, a big benefit that I see across the use cases is that you get significant reduction in the amount of code that it takes to do a complex application. And that has enormous implications for engineering because you can measure how many bugs you're going to have to how many bugs you have to fix as you maintain your code over time simply by the volume of the code. I'd like to show a timeline real quickly. 2002 is when MapReduce was really being done inside of Google. They published it in 2004. The Nutch team, which was doing open source web crawlers and web indexing, they took that paper and implemented Hadoop. That got picked up by Yahoo. And then the second Yahoo Summit was the one where you really started to have other commercial entities coming in. That was in 2008. An interesting thing here is that we've seen a big rise of Hadoop. And I've used Hadoop a lot. My teams have used this over the years. But yet, the trade-offs, the engineering trade-offs for Hadoop, they come from MapReduce back in 2002. It's over a decade ago. And when you look at the difference between now and 2002, the kind of hardware that we have is significantly different. You know, in 2002, there was no commodity hardware that had gigabit, or SSDs, or multi-core, or 128 gigabytes of memory. These things did not exist. So in around 2009, going into 2010, Spark came out of the Mesos project. It was an effort to show a kind of framework on top of Mesos, but a next generation beyond Hadoop. How could you really leverage the more contemporary types of hardware and come up with much better pipelining? Our project made it into Apache as a top-level project in 2014, earlier this year. But again, it represents about a decade difference from the origins of Hadoop. Another thing that happened over this same time period was that MapReduce is great for certain types of applications, batch processing, but that's not all you need to do. And so there are other types of specialized systems that have evolved to be able to handle these other use cases that are needed that MapReduce just does not fit. There's kind of a trajectory here. You know, it's like Google will publish a paper of how they solved the problem, and then other people will rush to implement it in open source. So you see Pregel going to Giraffe, say for graph processing. You see Dremel going to Drill. You see F1 going to Impala, Millwell and Storm for streaming processing. So the project I work on, Spark, the notion was to be able to, instead of having a lot of disparate systems, be able to have a common unified engine under which a lot of these use cases could work. Because this idea of having a lot of different types of clusters is also a risk. It's very expensive. It's hard to get your people to understand how to leverage all these different systems. It's costly to run them and administer them, and you pay a tax for moving data between them. So here's some papers about Spark. I'll return to this in a moment, but it really did have to do with a generation beyond Hadoop. Now, one minor problem about all this, functional programming is great, but how do we hire enough people who are expert already at working in functional programming? Scala, Clojure, F#, etc. That's an ongoing problem. Number 4, databases. This is a pet peeve. I'm old enough that when I was in grad school, they promised us that there was a new type of software coming out that we would be able to use for data we would only be able to work with it on paper for now because we did not have the software, but it was called SQL. And so this was back in the day when actually we were working with graph databases at the time, and things that looked a lot like graph. But there's been at least a generation of computer scientists that have grown up thinking that data implies SQL. And in the engineering teams that I've led, sometimes it's very difficult to get them away from thinking about that. So I believe very fervently that, SQL is excellent for being able to describe how to transform data, but we have to move away from that in the long run. And again, it's more about the thinking. There's a notion of computational thinking as a kind of educational rubric. And I believe that this is going to become very important for how we roll out big data. A step further, though, would be to think not just of data as an engineering issue, but as a business issue. And I was working on a book last year. It came out, actually. It's called Just Enough Math. Came out as a video, and then at O'Reilly, we decided to make it into a Docker image. So it's now you can pick it up as a Docker image if you want to run the code. The idea was this. Business executives need to understand more about the advanced math that they need for their business use cases, for their big data. So there's a problem. When we look in the US, the math curricula is still following a pattern that we set during the Cold War. The idea was that we wanted to have a lot of calculus required so that we could weed out the people who would be really good at building things such as ICBMs, weapon systems. And as a consequence, if you're in the universities in the US, typically there are a lot of people who get weeded out because of the calculus requirements. But yet when you look at what's required in business today to be able to leverage the big data frameworks, such as doing graph queries, the graph theory part does not necessarily require the calculus. But if you have not taken 2 to 3 years of calculus, you'll never see the good stuff beyond. And so there's a need for changing in terms of how we train people in business to understand that there is tooling beyond calculus, such as what you can do with really advanced linear algebra, what you can do with graph theory, what you can do with advanced forms of statistics, Bayesian stats, for decision making, et cetera, et cetera. These have a lot of implications on how we contend with problems in terms of supply chain, or maintenance schedules, or real-world business problems that have very little to do with calculus, very little to do with advertising and e-commerce, but it's what we need to contend with as big data expands. So I like to use this when I'm teaching about more advanced areas of mathematics, how it applies to business. A lot of the real-world data that you see is very messy, but yet when you clean it up a little bit and drill down into it, so many business problems can be represented as graphs. And so it's excellent now that we have a number of different types of graph databases, graph query engines, because these are a great first foot forward for business people to understand what's going on in terms of their operations. An interesting thing is that once you have a graph query being able to represent your business problem, it's usually not that hard to go from a graph into a sparse matrix. And once you're in a matrix, then it's not so hard to be able to apply a lot of functional programming and abstract algebra to come out with really high-performance solutions. That's a general rubric that I recommend. Okay, closing up on this then, number 6, approximations. In the 19th and 20th century, the emphasis on statistics was largely about being able to come up with an argument and being able to defend the argument. So we have this notion of defensibility, and a lot of the statistics were about goodness of fit tests to be able to defend one selection for a model. Now, that approach is interesting. There's a lot of excellent math, but it really set the tone for thinking about batch windows. And so as a consequence, during the 20th century, as computing has matured, coming into the 21st century, we have a lot of batch windows. We have too much thinking along these lines. There was a subtle point that was missed. What we're seeing now is a move towards modeling that embraces what's being called probabilistic data structures, or approximation algorithms, or sketch algorithms, pretty much all the same thing. The main notion is this: you can trade off errors. I apologize for my voice. You can trade off bounded errors on a problem to be able to approximate a given solution, but by using much, much less resource. So for instance, here there's an illustration from Ilya Katsov where, say, you could take with a countman sketch, you could take and track a number of frequencies, say, who are the best advertisers in a real-time bidding system. You could track them at scale, but by trading off 4%, plus or minus 4% errors, you can cut the memory cost for that application down by 2 orders of magnitude. And so this is a real game changer. If we can cut the memory that's required, we can start to fit the applications more so in memory and be able to run things in streaming and get rid of the batch windows altogether. At Twitter, there's a catchphrase that they use for this. They say, hash, don't sample. And it's how they leverage these probabilistic algorithms. In particular, there was a gentleman in Paris named Philippe Flageolet. Unfortunately, has passed away, but he was really the pioneer for a lot of this. And when you look at how these kinds of algorithms are constructed, again, it gets back to the abstract algebra. It gets back to the functional programming. They make a lot of use of, say, using monoids for reads and writes in parallel. It's a different way of thinking about programming, but it comes out with a very remarkable result. And the thing is that you can take intermediate values from your approximation algorithms, typically, and you can compose them together over different time periods. So if I need to have my day-over-day roll-ups, I can get those. If I need to have week-over-week, I can take 7 of those intermediates, put them together, and not have to run the query over again. If I want to have year-over-year, same thing. I can just compose all the intermediate values. So it adds to a lot more parallelism on multiple different dimensions. Here's a list of a few of them and some links. I'll have the slides available. But it's really a fascinating way of changing how we look at algorithms and writing code. And so I would suggest that we should start thinking about collections of data being based on these types of approximation algorithms. That's a new type of data type. And that's what we should be using at scale. Twitter, eBay, and others are definitely using this in production. And there's some resources for it, too. I'll leave those for the slides. OK, and one other kind of change of thinking has to do with notebooks. Again, I'm old enough to have lived through the spreadsheet era. In fact, I was working on a project doing some financial software on Apple II computers when I was in school, and it was only a matter of a week, I think. We heard about spreadsheets, and then suddenly we realized that all the software we were writing was ridiculous, that spreadsheets were just going to be so much easier to use, so we shut down the project we were working on. Spreadsheets were a real revolution at the time. They changed how business people could come in and use software without having a lot of programmers. It really represented a revolution in how we leverage computation. Now, there's a thing like this happening. I believe that notebooks represent a similar type of revolution in thinking about computing. Fernando Perez leads a project called IPython at Berkeley, and it's very subtle but also very, very, very powerful. The bottom line is that technology is not just about writing software, writing code. It's about people using that code. And in particular, I've made a lot of focus of the last few years for my work to be around enterprise data workflows. How do people in large businesses with large problems, with large teams, how are they able to come up with applications that can encompass those problems? As I see it, enterprise data workflows are now beginning to migrate towards the notion of notebooks, particularly cloud-based notebooks that have clusters backing them. I think that if you look at the big data tools that first came out, say from Yahoo, Facebook, et cetera, back around 2008, 2009, there were a lot of great tools. There was Pig, there was Hive, but there was a real emphasis on tools, building tools, using a tool. What we need, though, more is an emphasis on workflows. How do teams of people be able to handle and represent their process for their team, for their company? How do you combine the people, the automation, the process, the integration, all these parts that are necessary in business, not just how to use the tool? Now, Google has had a very brilliant approach of providing shared documents. I love using Google Docs, Google Spreadsheets, but as we see work with cloud-based notebooks, they begin to resemble a lot of the benefits of Google Docs. The idea is that an entire team can be working with one notebook. Everybody has a copy of the notebook in their browser window, and they can make edits and see it in real time. But the thing is that the different cells in a notebook can be computing SQL or Python or Scala. They can be generating different types of documentation. They can be viewing results that are generated out of the code, such as dashboards. It's a great way of having a team work together on code. As a case in point, if you haven't seen it, this came out, I believe, 2 weeks ago. It's Nature magazine worked with Rackspace to host an IPython notebook for publishing one of their articles. And I think this is revolutionary. The idea is that you would have the article, but you can compute some of the results of what the article is talking about. So if you want to go back in, look at the data, change some of the parameters, recompute to get a confirmation for yourself, this becomes possible now. I actually had the opportunity to be one of the alpha testers for this software. We used it for one of our tutorials at Strata, New York. O'Reilly has a similar program of where we're taking our books and generating them as a Python notebook, wrapping them in Docker containers, and then using that to be able to publish as a next generation kind of book platform, if you will. So, what does Spark have to do with this? And let me grab some water. So the notion of Spark, this was developed, like I say, 2009, 2010 at Berkeley. It's had an incredible amount of contributors coming in. I'll show a graph about that. But the gist of Spark is that there's a common engine underneath, which is leveraging the functional programming, as I was mentioning, leveraging the contemporary generation of hardware, doing a lot of in-memory processing. But on top of that, you also have different types of use cases. Spark SQL, streaming, MLlib for machine learning, graphics for graph computation, etc. And this way, you're able to avoid having a lot of different specialized systems and be able to do workflows that have these different parts, but all in a common piece of software. It leverages a lot of in-memory computing, and that's because these days you have much larger memory spaces. But if you have 128 gigs of memory, you don't want to throw that all into one JVM heap. You want to be able to have much more sophisticated ways of using it. So Spark is leveraging that. Another point is that in general, we find it's much easier to program. That's the feedback we get back from it. So for instance, if you look at the word count that ships with Hadoop, it's about 50 lines of Java. But the same code represented in Scala and Spark is 3 lines of code. And so we see this across the board where there's like an order of magnitude reduction in code volume that makes it much simpler for people to pick up some other team's work and continue it. As far as the number of committers, we've had exponential growth. We're now one of the most popular projects, one of the most active projects on Apache. And of course, a number of different certified vendors, certified applications, including our hosts here with Stratio. One of the very interesting patterns that we see emerging is to be able to take a distributed pipe, such as Kafka, put it through Spark, especially for Spark streaming, and then have something like Cassandra underneath. So Oscar was mentioning about NoSQL databases. I agree. I think that there's immense power in using NoSQL databases. Cassandra in particular is one we've worked with very closely. But the idea is that the NoSQL databases are a next generation beyond the problem that Google had back in 2002 of disks failing. Instead, Cassandra represents a really good way of having a robust file system that pairs very well with in-memory computing. Uh-oh, I lost memory. No problem. And one other point, in terms of Spark, why does it matter? One of the things that happened last month was we were able to set the world record for the terabyte sort. This was previously held by Yahoo. They had used over 2,000 machines, and they had followed the rules. It's called the gray sort challenge. So Yahoo had done this before. We were able to go in and use Spark with a little over 200 machines, 1/10 the size of the cluster, and we were able to run 3 times faster. So effectively 30 times faster than what Yahoo had previously had. So we're seeing much drastic increase in performance, again, by leveraging a contemporary generation of hardware and leveraging functional programming on top of this. Let me set that down. Okay. Now, as far as a company, Databricks has a product out that's called Databricks Cloud. And that's where these ideas come together. Databricks Cloud is about being able to have a browser window, a notebook, which is backed by Spark in the cloud. You have clusters running back there, but you don't worry about the operations of it. Instead, what you focus on is having your team look at the code, the ETL to bring your data together, whatever you need to do to prepare the data, perhaps some visualization, some insights, perhaps some machine learning to do predictive analytics, perhaps you're creating a dashboard, et cetera. But you have your team focused on collaborative tools, browser-based, backed by the cloud. Currently, we're starting this out in AWS, but we have announced that we will eventually be moving off to other clouds as well. And so we've been onboarding companies over the past year into using this Databricks Cloud product, helping them to understand how to leverage notebooks. Again, by taking advantage of what I've been talking about in terms of more of the advanced math, more of the functional programming, so that they can get the job done very quickly to leverage all the enormous amount of data that's coming in at them. I'll provide some resources here just as links. One is that part of the reason for being in Spain is we've worked out a developer certificate with O'Reilly, and we'll be holding this in Barcelona a little bit later this week. We'll be holding the first certification. And so I'm really looking forward to Strata. If you're going there also, I hope to see you. We also have a number of community resources about Spark. If you'd like to learn more, I'll leave those on the slide. The main takeaway is that we're happy to announce, I believe for the first time today, we have 2 new MOOCs about data science on Spark and machine learning at scale on Spark. These are produced in cooperation with the University of California, and they will be available on edX beginning in January. There's a few different books in publication now. Some of these are in early access. There's another one that I'll be starting when I get back home called Spark the Definitive Guide. But we're trying to get more information out there for people to take advantage of this. And there's a number of events that we'll be at too I wanted to list. And if you want to get a hold of me, I've got a newsletter here about different open source projects and conferences and whatnot. Anyway, thank you very much. I really appreciate it.